So let's get started. Remember last week, we're still talking about aldehydes and ketones, but we made this big pivot. We started by talking only about that electrophilic carbonyl carbon, and then last class we introduced this idea of this alpha carbon and how that alpha carbon is actually relatively acidic, making that alpha carbon a good nucleophile. All right, and so within this aldehyde or ketone, we have these two different sites, the electrophilic carbonyl carbon, but also the nucleophilic alpha carbon. All right, so one correction, kind of embarrassing little correction that I have to make from last class here. I called these reactions by the wrong name. I called them Claisen addition and condensation reactions. We will learn about Claisen condensations, but they actually use esters instead of ketones. These are what are called aldol addition and condensation reactions. The reaction's the same. It's exactly how we learned it. I just called it by the wrong name. Okay? But so we had these now we're calling aldol addition condensation reactions, where if you have like a beaker of, for example, propanol, and you put a little bit of base in there, you'll have neighboring molecules reacting with one another, some playing the role of the nucleophile, others playing the role of the electrophile. And so those will react with one another. All right? In these reactions, you use this NaOH. Okay, so what we're going to do first is talk about base choice here. Because NaOH is not a particular, it's considered a strong base, but in the world of organic chemistry, it's really not the strongest base in the world. It's actually a relatively weak base. And considering our acid-base reaction, if we have our aldehyde here, and I'm going to react it with that hydroxide ion. Everybody take a second and draw me my acid-base reaction here. All right, so my aldehyde is going to play the role of the acid specifically at that alpha carbon. So that's my hydrogen that's going to get attacked, leaving behind these enolate ions. And my other product, once that base accepts that proton, would be water. All right, now remember, back to acids and bases chapter here. We talked about comparing acid strength by looking at pKa values. And we can tell by looking at the acids on both sides of our reaction here which direction our equilibrium lies. Meaning I'm going to look at the pKa of my acid, which we said was about 17 for aldehydes. And I'm going to look at the pKa of my conjugate acid on the other side, water. The pKa of water is about 16. All right, so then according to these pKa values, what is the stronger acid? Water, right? The lower the pKa value, the stronger the acid. And remember, the stronger acid wins. So this reaction right here actually favors the reactant side. So we're using a relatively weak base for the proton that we're trying to remove here. All right, and this turns out to be an important condition for these aldol addition and condensation reactions. We don't want to use too strong of a base. We don't want everything to be converted to this enolate ion here. We only want a small population, so then they will react with their neighboring molecules. All right. So in contrast, we talked about another type of reaction, these alpha carbon alkylation reactions, where we can take that same aldehyde or let's just take that same aldehyde, propanal. And we react it with a base. And we just said base at this point, because we're trying to create that enolate ion. And so then we turn around and we react this with some sort of an alkyl halide, a good electrophile. And we get this alkylation reaction. Putting, in this case, 2 new carbons on that alpha carbon. So this was this alpha carbon alkylation reactions. This was actually the first type of reaction we were talking about with those nucleophilic carbons. Okay, now importantly, how am I going to prevent this from just reacting with itself, right? Our choice of base we have to be really clever for. If we use too weak of a base, all we're going to get is that aldol addition product, where it reacts with itself. This aldehyde is just reacting with itself. So for our base choice here, we're going to have to choose a very strong base. All right, and there's 2 different options that we can choose for this very strong base, or in practice that they use. The first one is one that we've seen before, our sodium hydride. All right, the other one that's commonly used is what's called LDA. And this is one of these negatively charged nitrogens, these really strong bases here. But those are also good nucleophiles. So to prevent it from being a nucleophile and only a base, it's got these big alkyl groups coming off the side as well. Let's just leave them as R groups, because honestly I don't remember how long they are. Right, but this is one of our strong, bulky bases. So it can't be a nucleophile. It's just too big to be a nucleophile. So it's just going to be playing the role of a base here. All right, so then given what we just discussed, let's just practice here. Let's say that I take acetone. And in one beaker, I'm going to put in some sodium hydroxide. And then in another beaker, I'm going to use that really strong base, LDA, along with some sort of alkyl halide. What's going to be the difference that I see in these two here? For my weaker base, I'm going to see that aldol addition product, where I have one acetone molecule playing the role of the nucleophile, reacting with another acetone molecule at that carbonyl carbon, creating that aldol product. Okay. These reactions here, they're with sodium hydroxide. Specifically, the solvent that they use is in ethanol. Okay, this is another sort of little trick for decreasing the amount of substitution product that you get. If you use an aqueous solution, you would get some of that Chem diol product that we talked about, where these ketones and aldehydes react with hydroxide to form, I guess we just want to put it down. Let's go for it. So if we used NaOH in aqueous solution, we would get the hydroxide ion playing the role of the nucleophile. So we would get that Chem diol product. If we use it in ethanol, it really can't form those hydroxide ions that are playing the role of nucleophiles, so it just plays the role of a base. Okay? And if instead we use that strong base LDA, what we're going to do is form every bit of those acetone molecules, every one of them gets converted into that enolate ion, which if then we turn around and react with our alkyl halide here, we'll get a substitution reaction, putting a methyl group on that alpha carbon. All right, so for our weaker base, we get that aldol addition product. For our stronger base, we get that enolate ion. All right, and we talked a lot about those enolate ions last time, so let's just remind ourselves. Okay, we're going to take this. What is that? Go away. Let's put some LDA in there so we get 100% conversion to that enolate ion. It's going to deprotonate that alpha carbon. Okay? But we said that why this alpha carbon is so acidic is because this enolate ion is not just this one structure. But if we're good, we got to draw two resonance contributors here. All right, so everybody take a second and draw me my second resonance structure. So this allylic lone pair can come down. Forming a double bond here. And now I have that negative charge on that more electronegative oxygen atom. Okay, so these are both the resonance contributors for this enolate ion. We said, just a caution, right? We said that the one on the left, this one's the more convenient one in our reaction mechanisms. But the name enolate comes from this one here, because this is the more stable of the two contributors. And keeping in mind both of these is going to be important in understanding the chemistry of these molecules here. All right? So at this point, we've got these two very strong bases. For right now, we're going to consider them to be the same thing. We're going to complicate things here in a little bit, all right? But we got these two strong bases that we can use in our alkylation reaction. Okay. All right, so another one that we're going to go back and review that we talked about are these alpha carbon halogenation reactions. All right, and what we talked about were under acidic conditions, how we can take an aldehyde or ketone. Let's do cyclopentanone. All right, and if we react this with bromine under acidic conditions, you don't form an enolate ion. You instead just form an enol. Everyone take a second and draw me the structure of this enol that's going to form under acidic conditions. Okay, and to be clear, this ketone and enol are in equilibrium with one another, what we call a tautomerization. So the name enol, I have a carbon-carbon double bond right next to an ol, an alcohol group. All right, and this is what would have been our nucleophile okay, our double bond here is what reaches out and does the attacking. Oh, whoops. All right, if I'm going to be good with my mechanism here, I got one more deprotonation step. Don't let me forget your exams at the end of the day today. But one thing that's y'all gonna drive me nuts on is something like this. What the hell is that? You can't do arrows like that. Your arrow has to start at a pair of electrons. This little lazy shorthand business, you're gonna get marked off for nickel and dimed all over the place. Be putting your arrows in the proper place. The arrow has to start at a pair of electrons. You can't just draw it wagging out in space. My base of my arrow at a pair of electrons, the head of the arrow at an atom. All right. The other thing, we can't have hydrogens just jumping off, right? You can't just have a hydrogen that's just going to fly off into space. Something's got to be accepting that hydrogen. There has to be a proton acceptor. That's why in chemistry, we do not use the H+ For acids, we use hydronium because we're good and we're keeping track of the fact that these things don't just fly off into space. They got to be accepted by something. This is a biology kind of shorthand here. All right, so then my final product is a brominated alpha carbon of a ketone. All right, and importantly though, trying to stress here that it is this enol that is playing a very important role in our reaction here, right? It's the creation of that enol that allows that alpha carbon to get brominated. So here I use this symmetric ketone, right? It wouldn't have mattered which alpha carbon I chose. I would have gotten the same product. Okay? So now let's start. We're going to do the same ketone here, but I'm going to throw a methyl group on one of those alpha carbons. So now if we do our bromination reaction under acidic conditions, we would have two possible products that we could get. We could brominate the carbon with the methyl group, or we could brominate the other carbon. All right, so what is the major product? All right, now bromine itself does not have a preference for a more substituted carbon or a less substituted carbon. These carbon-bromine bonds are the same strength regardless, okay? So in order to figure this out, we're going to have to first draw our two possible enolate ions, right? Just like we did first, or not enolate, I'm sorry, enols. Just like we did up here, the first step were to draw those enols. So let's take a second. We got two possible enols that we can draw here from this particular ketone. So if here's my ketone, see if you can give me my two enols that we would get under acidic conditions. All right, so starting with our ketone, we could get two different enols depending on which side our double bond forms. So we could have it over here. Whoops. All right, that would lead to this product. Or we could have our double bond form on the other side, and that would lead to our other product. Okay, So looking at these two enols here, these are what would give us our two different products. Which one do we think is the more stable of the two enols? All right, let's vote. Who thinks it's the one on the left, A, and the one on the right, B? So why do we think it's A? Substitution, right? So this is the more substituted alkene. Which means that this is my major product. Right? So the more stable enol is the more substituted enol, and that will lead to your major product in this reaction. Okay, so again, we got to think about that enol intermediate to understand these reactions. Okay. So we can just say the more stable enol, i.e. more substituted, gives the major product. Okay? So we talked about these reactions under acidic conditions. Under acidic conditions, we have this enol that's formed that's going to play the role of our nucleophile. If we have an asymmetric ketone, the more substituted enol that forms will give us our major product. All right? But now let's talk about this same reaction here, but under basic conditions. So alpha carbon halogenation. All right, but there's no reason why we can't do it under basic conditions. Under basic conditions, we also get a good nucleophile, our enolate ion. Okay, so everybody take a second. Give me my enolate ion that forms under basic conditions. Cool, so we get our enolate. We can use the more convenient one for our mechanisms here where we have that carbanion ion. All right, and just like before, this can play the role of the nucleophile. It's an even better nucleophile than our enolate ion, than our enol. And so under basic conditions, we will also get this bromination of our alpha carbon. Okay, so actually real quick, let's just remind ourselves this is now basic conditions. All right. Under basic conditions though, you can't stop it here. it's actually going to go and react again and again and again. Okay, so let's just real quick, let's take our product from this first round here. And we're going to, again, form an enolate ion under these basic conditions. Okay. This second reaction, after you put the first bromine on, it will actually react a second time even faster. All right? And that's because we have this enolate ion here. Okay. Our carbanion is stabilized by that halogen. Halogens are very electronegative, right? The carbon's not really happy having all that negative charge. It's stabilized through resonance. That's why we can deprotonate it to begin with. But if there's a bromine on there, it just further stabilizes that negative charge. Bromine's very electronegative. It has this induction ability, right? So it's pulling some of that electron density away from that carbon and onto itself. So this carbanion is stabilized by that halogen through what's called induction. All right, so the bottom line is you don't just get one bromination event, you will get every single one of your alpha hydrogens replaced by bromines. All right, so under basic conditions, this bromination reaction is just going to keep going and going and going until every alpha hydrogen has been replaced by a bromine. Okay, so under basic conditions, all of your alpha hydrogens are substituted. All right, so because of that, there's a special case here when you have a methyl ketone. What are called haloform reactions. All right, so first of all, I'm going to take this and we're going to put it under basic conditions in the presence of bromine. Everybody take a second and tell me what my product would be. So because we're under basic conditions, I'm going to replace all of my alpha hydrogens with bromines. But now this is under basic conditions. So my hydroxide ion, now that it's done being a base, can play the role of a nucleophile. Where's it going to attack? That electrophilic carbonyl carbon. All right. This would give us that tetrahedral intermediate. Okay, but this tetrahedral intermediate is a little different than the ones that we've been looking at up until now. And we're actually going to see this kind of a lot in the next few chapters here. We start talking about these carboxylic acid derivatives. So I have my alkoxide ion. I have that OH group that just attacked, but I also have this carbon with these 3 bromines here. And what's different about this tetrahedral intermediate, remember we said that those halogens help stabilize that carbanion. I have a maximally halogenated carbon here. So this thing here is a good leaving group. It can leave, take that pair of electrons with it, and that will be a carbanion, but that carbanion is stabilized by those halogens. Good leaving group. All right, up until now, every time we've seen a tetrahedral intermediate, it didn't have a good leaving group. So it was kind of stuck at this alkoxide step until you went along and added some weak acid or something to protonate that oxygen. We're going to see in a lot of these other reactions, you get this tetrahedral intermediate, and there's a good leaving group on there. So what's going to happen is this pair of electrons is going to come down and kick off that good leaving group. Right, that alkoxide pair of electrons is going to come down and reform that double bond and kick off that good leaving group. Okay, so then give me my product here that we would get following these arrows. All right, so we can convert a methyl ketone into a carboxylic acid using this haloform reaction here, right? Bromine in the presence of a base. Because you get your normal alpha carbon halogenation reaction, but then you've created a fully halogenated carbon which can act as a good leaving group. Cool. All right. So now let's go back to these alkylation reactions and these 2 bases. What's going on here? All right, what's the difference between the 2? Okay, so we said the LDA was a strong, bulky base. Sodium hydride is a strong, small base. All right, so what we're going to see is that we can sort of tune our reaction conditions. If we start out with an asymmetric aldehyde or ketone, I guess really just asymmetric ketone. Let's do. Okay. If we use our bulky base, the LDA, at low temperatures, we're going to specifically form the enolate on the more accessible carbon. This is what we would call the kinetic product, because we're at low temperatures. LDA is a very strong base, but it's big and bulky, so it's going to favor the more accessible carbon. Or we could instead use our small base, the sodium hydride, at high temperatures, and this would lead to the thermodynamic product, the more stable enolate ion, which is going to form on the more substituted carbon. Okay, and to be clear, this is our kinetic product because this is more accessible to our bulky base, so it forms faster. That's what the kinetic product is, the one that forms the fastest. Okay. Why is this one the thermodynamic product? I want you to show me using that other resonance structure for my enolate ion. All right, so we can use this resonance structure to illustrate that this one is our thermodynamically favored because it gives us the more substituted enolate. Okay, so there are these two strong bases that are traditionally used in these alkylation reactions. You can either use LDA or sodium hydride, and which one you pick is sort of dependent on what product you're looking for. LDA is used at low temperatures to give us the kinetic product, where that enolate ion forms on the more accessible carbon, and sodium hydride is a small, strong base that's used at higher temperatures to give us just the more substituted enolate ion. All right, so then if we take this same thing, let's just finish this off. You guys are going to give me my products in the following alkylation reactions. LDA, low temperatures, 1-bromopropane, then we'll do our small base at higher temperatures with that same alkyl group, same alkyl halide rather. right, so we got these two alpha carbons. The more accessible one is going to be favored under these kinetic conditions, and the more substituted one is going to be favored under the thermodynamic conditions. So we'll get alkylation on the left-hand side at low temperatures and alkylation on the right-hand side at high temperatures. All right, and again, just to kind of bring it back to where we started our discussion, if instead we didn't use one of our super strong bases, but just used the meh sodium hydroxide, then we would get that aldol addition product. All right, so now we're going to actually talk about the Claisen condensations. These are very, very similar to our aldol addition reactions. But using an ester instead of an aldehyde or ketone. All right, so we're going to take an ester All right, so an ester's got that carbonyl group, carbonyl carbon, but there's necessarily, it's like a carbonyl, a ketone, and an ether mixed together. Okay, that carbonyl carbon is necessarily bound to an oxygen, and there's got to be some carbons over here as well, otherwise it would be a carboxylic acid. All right, so how many alpha carbons are there in an ester? Just one, right? Because there's necessarily an oxygen on the other side here. So if we take this thing and we treat it with base, we're again going to see that deprotonation of that alpha carbon, creating that enolate ion. All right, and we'll talk about the choice of base here in a second. They're very clever with the base that they use in these reactions. Okay, but so now what we're going to see, so we see the same sort of alpha carbon deprotonation of an ester in basic conditions. All right, so what we're going to see in these Claisen condensation reactions is, again, one of these molecules is going to play the role of the nucleophile. The other one is going to play the role of the electrophile. That electrophilic carbonyl carbon and that nucleophilic alpha carbon. Okay, just like we saw with our aldol addition reactions. All right, so let's just go ahead. We're going to make our nucleophilic enolate ion here. We're going to have our nucleophile attack our electrophile. Everybody take a second and give me my intermediate here. right, so again, after we have our nucleophile attack that electrophilic carbonyl carbon, we get that tetrahedral intermediate. Okay, but again, unique to what we have seen previously. Now our tetrahedral intermediate has formed on an ester, and our tetrahedral intermediate has this good leaving group. It's actually not a great leaving group, but it turns out it's good enough, all right? So everybody take a second. Considering that that's a good leaving group, draw me the product that you would expect from these Claisen condensation reactions. Okay, so that pair of electrons will come down and reform that carbonyl group, and I'll have kicked off that leaving group. So if we were being good here and we draw our other product, it would be this methoxide ion. All right, and we called this thing a good leaving group. That's kind of a little bit of a lie, right? It's a strong base. We don't consider those to be good leaving groups. All right, so then how are we able to kick this thing off here? Well, let's look really carefully at our, the previous step and compare it to this step here. Both my tetrahedral intermediate and my leaving group are an alkoxide ion. All right? So, from the standpoint, what's up? Did I mess it up? So let's see. Let's just count. So 1, 2, 3, 4 from my original ester. 1, 2, 3, 4. Oh, yeah. Shit, I am missing a carbon. This now needs to be bound to this, which is my carbonyl carbon. Good catch. Count carbons. Yes, excellent. Okay, take my own advice here. Because yes, now 1, 2, 3, 4. Okay, my product was correct. My original one wasn't. Okay. Okay, so anyways, going back, we're going to compare our leaving group with our intermediate here. All right? Both my tetrahedral intermediate has an alkoxide ion, and my leaving group has an alkoxide ion. So from an enthalpy standpoint, delta H is equal to 0. There's no new bonds have been formed that are less favorable than bonds broken. I have an oxygen with a negative charge here and an oxygen with a negative charge here, right? Both of them are equally kind of mad. Two strong bases, okay? So then what is it that's going to be driving this little piece to break off here? The other component of whether or not crap occurs in the universe, the entropy. Right? Breaking off that little piece is going to be entropically favorable. Taking this molecule and breaking it into two smaller fragments, that's an entropically favorable event. So this isn't a great leaving group from an enthalpy standpoint, but it matches the exact sort of unfavorable negatively charged oxygen that I had in my intermediate to begin with. And you get this entropy benefit from kicking off that little piece, right? So even though we really wouldn't call this a good leaving group, we'll call it a meh leaving group, it still plays the role of a leaving group in these reactions. Okay? So first of all, count carbons. That's a great way to check your product. Okay? The other thing about these condensation products that you can use to double check is the spacing of these functional groups will always be the same. And this is true for the aldol addition and condensation reactions as well as these here. If I start counting at my ester carbonyl carbon, 1, 2, 3, my new bond, well, first of all, I'll always have this 3 carbon spacing of these 2 functional groups, and my new bond will always be between carbons 2 and 3. All right, so just kind of an easy double check for both the aldol addition condensation and our Claisen condensation reactions is the spacing of these functional groups. Okay, what makes these reactions challenging is, again, we're making new carbon-carbon bonds. We have these big, ugly products. All right, so practice is important here. Let's just do another one. Oh, before we move on, I said that they were clever about their choice of base. The base that they choose is going to match that alkoxide that you kick off, right? That way you're always replenishing that supply of base as this reaction is going on. So these will specifically use these alkoxide ions, RO, okay, and again, R matches your ester functional group. So in this case, you would use a methoxide as your base, because that's what's going to end up being kicked off in this reaction. All right, so let's just practice another one of these condensations. Okay, tell me what base we should be using, and then give me my Claisen condensation product. All right, so first of all, for the base, we're going to use the ethoxide ion, our 2-carbon alkoxide ion, because that's what our ester is a 2-carbon ester. And we're going to be reacting the alpha carbon of 1 with that electrophilic carbonyl carbon of its neighbor. All right, and you could just give me the product. For these particular reactions, I think that it's kind of helpful to draw out your mechanism, all right, or in particular your intermediate. You certainly don't have to, and as you get better at it, you might not have to, but it can be helpful to see what's what. One more. All right, so let me just make sure. 1, 2, 3, 4. 1, 2, 3, 4. Okay. All right, and then again in these reactions, this pair of electrons is going to come down and kick off that ethoxide leaving group. Okay, I'm going to kind of twist this around into a little bit more natural of a configuration here. Okay, so importantly, your nucleophilic ester is going to be fully represented in your product. Every carbon from that nucleophile should be found in your product. So boom, these 1, 2, 3, 4, 5, 6 from my blue, my nucleophilic ester are in there. But your electrophilic ester is going to lose that alkoxide group. So I'm only going to have this half of my molecule in my product, these 4 carbons. All right, and again, we can double check by counting carbons, but I should also see that 1, 2, 3 carbon spacing between my 2 functional groups, where my new bond is between carbons 2 and 3. All right, so another just kind of easy check. Since we got such ugly, complicated products, a second check to make sure that we've drawn our structure correctly. Cool. All right, we're going to call it there, and everybody, you can put away your stuff, and we'll do our exam viewing.